Hello, good morning to everyone. After a long day, of discussions on the Neuromorphic Computing project that we are having on the international consortium, we are having this broadcast on neuromorphic computation and why it is needed and how it is useful, its advantages and benefits. Just a brief review. This consortium, is sponsored by the European Commission EIC program. And the project is abbreviated RESPITE. We have participation from Single Quantum of Netherlands, Fraunhofer, University of Ghent, TU Delft, UGRO, Oxford University, and TÜBİTAK is partner of this project. So it's quite a large consortium of participants. We are trying to make use of the particular expertise of each of these groups. To start with, why do we need neuromorphic computation? I think we need to rethink computing in a way that is both physically intelligent, that's scalable, that's energy efficient and fast. Especially given the current paradigm of artificial intelligence, large language models, it is expected that close to 20% of the electric energy consumption will be due to running, these kind of models. So new computational paradigms are needed to circumvent the high energy consumption, the heat generated, and speed, the current CPU and GPU-based computational frameworks. Neuromorphic computation, in particular, encompasses and it's inspired by the brain's cognitive functionality. So, in order to be able to implement neuromorphic computation, we need to be able to understand how neurons work, how they are interconnected in the brain, and in general how the brain works. And hopefully, as a result of this research efforts, we'll be able to achieve a new computational paradigm that would provide us a framework that's both energy efficient and fast and scalable. So that's why we are gathering together in this program and in this project. So I would like to get the opinions, of the participants as to why we need neuromorphic computation and what is the history behind it. As far as I remember, the starting and coining the word neuromorphic computation goes back to 1980s to Caltech in the Cairo Meet. As a matter of fact, when I was at Caltech, he was the faculty member, and the first book on integrated circuits, VLSI, the name of the book is VLSI, I vividly remember, was authored by Carol Mead. And at the same time, he coined the word, I believe, neuromorphic computation the first time in the early 1980s. So I would like to direct this question to our participants. Why neuromorphic computation is important and how did it start? So anybody would like to say a few words on this?
Yeah, maybe I want to start. I mean, we know there are very powerful artificial intelligence today. It's very powerful, but it's also taking an enormous amount of energy resources. And we already see in the past our main architecture for computers was CPU-based with memory and CPU separated. We already know from the brain that the different locations gives a lot of energy costs, so you can better integrate them to go to in-memory computing and maybe into neuromorphic computing. But you see also industry is already looking for better hardware, and they already found out that the graphical processor unit, GPU, were much better to do the artificial intelligence, but it's better, but it's not optimal. We still know that we need new hardware, and we know it because current tasks like artificial intelligence, particularly for pattern recognition, we know that our brain is extremely efficient with 20 watts only using. And we know current systems, when we have to program them, it takes a lot of energy to program it. And that is very inefficient. And in the end, we have to go also to widespread use. And currently, the one of the main limitations is the energy costs for all kinds of systems. So we really, and we know, so it's not some speculation, we know from the brain that we have some, say, good ideas that it can be orders of magnitude more energy efficient in some tasks, but even we don't have to completely emulate the brain because the brain is also in some ways extremely slow. So we can still find an optimal way to go to low power consumption, but still very powerful. And then we can outperform. And then we have something which is in between. Say we have the current computer paradigm, it will definitely stay because it's very powerful. We have in the future maybe take still a bit more time quantum computing, which is also powerful for certain specific tasks. But we definitely need in between something which is neuromorphic computing or cognitive computing, which is particularly optimized for certain tasks, which is not possible with either of the two other technologies. And I think there is a lot of room for hardware development because it's not in the software that we can solve it. We have to solve it in the end also in the hardware stage.
So in-memory computation, I believe, is the key word over here. Because the classical von Neumann architecture, bottleneck over there is between the computation and the memory units. Because when you do computation, you need to exchange data between the memory units and the bus that you use to communicate in between.
It's slow,
it gets slower and slower, and the bottleneck is there. So in
both the memory and the CPU are quite optimized. They are quite good at the moment, but particularly all the traveling of information back and forth, that is the most problematic development.
Communications channel is the bottleneck. And in-memory computation basically eliminates.
Yeah, and what is nice about in-memory computing and particularly matrix vector multiplication, that if you can do in-memory computing, for instance, in a crossbar array, it already gives you directly in the crossbar array all the weights of a deep neural network. So if each chip, for instance, is a crossbar array, or even there are ways to stack different crossbar arrays into one chip. Each crossbar array is a one layer potentially in a deep neural network. So it's in principle also a nice way to, in this ways with in-memory computing, with crossbar arrays, if you have then one layer of a deep neural network, and if you can stack them and scale them, which we also know from certain technology like Intel Optane, it's a crossbar array based on phase change memory, it's really working. And then, of course, you currently do it digital, but maybe also we have to go to multi-level and then analog type of in-memory computing. So then that is really also required.
In addition to the speed advantages, of course, the other major advantage is the energy consumption. You know, you can achieve in the order of attojoules, of switching time, switching energy using neural computation. This kind of architecture that we are working on. And it is very comparable to the energy consumption of the brain. It's also in the order of, I believe, 5 to 6 joules also. The total energy consumption of the brain, as you mentioned, is around 20 watts. So if we can achieve that kind of scalability and together with the in-memory computation, that would be a great achievement.
Yeah, one of the solutions is, of course, also that's why the brain is efficient. It uses with spiking. So in the end, it's not the continuous signals, which all the time cost energy. It can do it spiking, and then it's also very important. You need some non-volatile storage. So if you all the time need to refresh your data and it costs a lot of power, this is not what you want. You want to have spikes, store information, and then if you don't need to alter the weights, you can keep it there for even quite some long time. And that is really saving a lot of energy.
Yes, exactly. Any other comments in this regard?
Yeah, I can also agree. We as Fraunhofer HHI in this specific project look at the simulation of such hardware systems. And the interesting part for us is certainly the capabilities that this offers. We are, again, efficient deep learning. This is, for example, our research group. We have looked into energy efficient AI inference training, but also into efficient transmission. However, only up to now in this kind of more classical paradigm. We have the huge GPU, CPU-based machine learning algorithms. We looked into, yes, we can make FPGA solutions, for simulating those matrix multiplications, etc., but only to a certain degree. Yes, you save some energy in this part. And the good thing about this, for example, we are looking into even compression of neural networks. So we transport neural networks just as a fraction of their size. That means, but that still means in the sense of, for example, language models that are used nowadays, where you have billions of parameters and you have some gigabyte of data. Yes, you have then some megabyte only to transmit. This is still, although it's a fraction of the time, and the underlying neural network compression standard, which has been standardized the year before, which we are quite proud of to do so. So in terms of what you mentioned, in terms of communication, we are already doing something, but still this requires a lot of processing. And if we look into, classical approaches, we see the usual development, the networks are exploding, the capabilities and the tasks they offer are incredible. So every area is now more or less using neural networks, artificial intelligence to some degree. People also trying to shift this towards edge devices in like federated learning, where you have also a lot of transmission, but all these devices require more and more energy. I mean, they gain more capabilities, but they also require more energy. And this is really amazing, and not amazing, but we really need new ways of hardware to keep up with the speed, because as you know from the news, big companies are already discussing additional power plants to feed their neural network architectures. Yes. And this is something, I mean, foreseeing the current developments of technology in this area, in the AI area, this is, to my opinion, not feasible. We definitely need to do something. And for us as a partner, this new possibilities of neuromorphic computing, they offer tremendous capabilities.
Yes. These days, the large language models, the introduction of NVIDIA GPUs and huge, 50,000 GPU server farms, and also the DeepSeek, that was currently introduced, in China. The paradigms of computation is changing very rapidly. I wonder, what will happen in the next coming even weeks, not years, but even weeks. How the environment, of artificial intelligence, large language models, and computation will change. And this neuromorphic computation paradigm that emulates, how the neurons work, I think will greatly impact, the way large language models and artificial intelligence computation will be handled in the future.
Yeah.
What is one issue is, of course, currently everything is still based on the standard CMOS processing. And of course, we still have to see if new emerging technology can compete with that. But still, even on the basis of CMOS, you can do completely new architectures. But you can even go beyond CMOS and then want to go to totally new materials than the current transistor-based system. And then find new emerging, like in-memory computing elements, like phase change memory I'm working on. But there can be other, it's not a matter of that one technology is maybe the best. We have to find new materials where we can do this in-memory computing, and then that could be very helpful. And it can also be other solutions, maybe in the future, ferroelectric memory or magnetic memory, which can help.
And many other.
Yeah. In general, we need memristors, and memristors can be made from maybe different types of materials or different architectures, and then we have to find the memristors which can then be these weights.
Are there any ideas as to when this neuromorphic computation idea, was initiated? I remember, Carver Mead, in 1980s, but any other opinions on when this actually started?
Yes, I think important developments started in the 80s, but you see it many times in technology. Some basic ideas are there, but then to really be able to do it, you need also to have other technologies getting up to par with it. And you see also we had the trend in the 80s, we were analog, and actually we say we can do it at that time, which we could not do. We have now through decades where we are digital, and we keep, of course, digital because it's very powerful and robust. But in the future, we'll go back to new analog technologies. And I think the new analog, which will be really helpful also for doing this. But in the 80s, technology was definitely not there to do this type of massive work. And you also see these large language models need really the current powerful computer resources to be really useful. And it will only grow in the future.
I mean, this kind of large-scale computation was not there, but I remember the idea of VLSI, very large-scale integration on the chip, was starting to emerge in this. Okay, any other interventions from our audience? If not, I'll switch, to another perspective for our discussion. Let's discuss a little bit about our project, the RISC-V project that's sponsored by the European Commission under the EIC program. And I mentioned our partners. It's a quite diverse participation in many European institutions with their own expertise, each one of them. I must say, the original idea, I think, was conceptualized by Iman and Ethan in the single quantum. Right now, I think Iman has switched to TÜBİTAK. He's moved, to another institution. He had invited us, TÜBİTAK, to this program, and he asked us, what kind of contribution we could make in this. Before participating in this fight, we had similar projects at TÜBİTAK, both in simulation and characterization of these kind of neuromorphic devices, in particular phase change memory devices that are heavily involved in the RISC-V project. So we were willing to participate and contribute in this program, and we are happy as TÜBİTAK also to be part of this great program. And the general idea of RISC-V is we again emulate how a neuron works, but the weights of the neuron, dendrites in the actual neuron, are modeled or actualized through PCM, phase change memory devices. PCM has different states. It can be in an amorphous state and also a crystalline state. When you excite a PCM material in crystalline state with a heat source, it could be the heat source could be light, laser beam, or could be an electricity. It switches mode. It switches from in between amorphous mode to crystalline mode. And crystalline mode is very conductive, whereas the amorphous mode is insulating, almost insulating. So these represent the states of the weights of the neuron, basically. The inductive mode, the crystalline mode could represent one state, and the amorphous mode could represent another state, another weight of the neuron. And then the activation function is emulated through a superconducting Joule switch, where single quantum, is producing, manufacturing. So that's their major contribution in this project. And this is how we model a neuron through phase change memory weights that represent the dendrites, of the neuron, and also superconducting Joule switches that represent the activation function. And then once we design and produce these neurons, we are planning to form neural networks, multiple stage neural networks out of these neurons, and then solve real-life problems like pattern recognition, signal identification, and many different applications of neural networks that could be applied in real-life problems. We'd like to implement on this chip, hopefully neuromorphic chip that we are designing. So any ideas on how our RISC-V program, neuromorphic computational model, differs, the advantages of this model with respect to other classical computational paradigms and also other neuromorphic approaches?
Yeah, I think maybe I can again tell something here. My name is Bart Koort, professor at the University of Groningen, also particularly expert on phase change materials and phase change memory. I think you also have to mention an important part, and that is that single quantum make these pixels, which are single photon detectors. and they can detect a single quanta of lights, photons, which is light connected. And then this is into a detector, and then the detector has to be, the signal has to be processed, what kind of pattern comes on this detector. And that goes then via the neurons and the synapses. And that all these three elements have to be connected together. So first you have say something like the eye, we get the light in, and then the light in is on different pixels and it's processed, and then it has to be processed via a deep neural network, which consists of, because all the single photons are detected at say ultra low temperatures, and also the neurons operate then at ultra low temperatures. And then also that is one of the challenging parts. The weights also have to be working at ultra low temperatures. So all these things have to work together.
Yes. So that makes the implementation quite difficult and challenging.
Yeah,
because the entire device should be operating in a cryogenic environment in few degrees, Kelvin, to be successful. Any other contributions on how the respite program, will we think will contribute to the neuromorphic computation paradigm?
As I said before, probably for us, it is quite different from what we are usually doing when we are developing applications still on a classical basis for neural networks in those different areas with those millions of connections, etc. So the challenge for us was really to look at neural networks, also to simulate neural networks in a new way for us, i.e. breaking down neural networks almost to its very atoms. Atoms meaning individual neurons, simulating very different approaches, for example, for really to be used with analog circuitry, to be used, as you just pointed out, with PCM material and all those components that Respite will bring together. And that was already one thing. We had new ways of, or are currently investigating new ways of investigating really the hardware requirements of this, different noisy conditions that come into this, different fabrication errors that we as a, let's say, pure simulators or more in the area of AI experts did not work too much before this. Yes, of course, we are transmitting data in a lossy way, but more in a mathematically lossy to a degree where we say we still want transparent performance of a neural network, meaning that whatever matrix is behind it, be it for pattern recognition, be it for whatever task, language model perplexity, for example, take this, is in a reasonable original range. That means that from the accuracy of a compressed and decompressed network, you still want to be able to perform the same task, right? If you had an accuracy for 91% of correctly detected images, you still want to be able to be at 91, or let's say maximum 90.5 or some in this area. So those types of errors or of kind of noise we already envision, but that's currently something where we also see the interesting part, the future and the challenge, since those systems provide such low energy consumption, to really like almost take apart complex neural network, look at the very basic building structure, almost to go back to the very first neural networks that were introduced in the 1950s and later not followed because there were simply no capabilities of further developing such technologies and then building it up from there towards that system. So that's, for example, our view and our, let's say, also appealing part from what the project offers to us.
We discussed the potential impact of neuromorphic computation to the general artificial intelligence related computations and its impact, its advantages. But how exactly close this technology to commercialization? In the morning, I remember in our sessions, we discussed there is Intel and IBM, they have their chips that are introduced. but not exactly at a commercial level, but sort of in an experimental stage. How exactly are we far from commercialization, and where are we right now? And what are the major players that you think will come up? Any interventions from the participants on the screen? Okay.
I think the platforms, of course, like I mentioned a bit before, you have either CMOS-based platforms, and then already the architecture is really optimized to do neuromorphic computing, for instance. And that's already possible with current CMOS technology, but then you go away from the current architecture and like you go to develop a new architecture. And that's done by, I think, many big companies like IBM, Intel, other types, Samsung are working on it. So that's one possibility to follow the CMOS route. And the other route is, of course, to really go to new types of computing architectures with new materials. And then I don't know, not so many companies. I know particularly IBM Research, which is looking, for instance, to phase change memory. There are other more from university-based in France, also more magnetic memory. But I think from commercialization, this is difficult to really compete currently. So you need another, maybe can be done in like 4 or 5 years, but then maybe chips can come onto the market, which maybe can do some important part of the task, and it will not really directly be disruptive, that it can replace current, say, ways the large language models are processed or other patterns. Be done. But it still starts to work parallel, and then if it's developed more and more, in the end it can take over, and that can take maybe another 10 years.
And how long do you think that will take? Maybe like another 5-10 years or so?
Yeah, I think in the orders of 5 years. 5 years to be also interesting, to work parallel, another 5 years to be maybe even become taking over. So 10 years from now, maybe we will have, but that's maybe a general perspective.
But do you think that like there's always, or not always, but there's this immensely growing pressure of energy hunger of AI? Do you think this will simply force such solutions to emerge? Because I remember if you compare it to, let's say, the classical thing of quantum computing, you know, the premise of quantum computing is there already long, and people are discussing how many quantum qubits they can now arrange, which is relatively slow also in the terms of, I think from that point, this is already quite more, but the question is, will it be just the sheer demand that energy cannot any longer be, you know, sufficiently supported for all the new AI-based applications, that people simply have to invest more and say we now have to really go to this paradigm, and now, you know, coming up with this very low.
Because also in the end, maybe new nuclear power plants or other power sources will be found too. So always people will continue to find as much as possible resources as possible with old, let's call it old technology, although they are very advanced. But in parallel, there will be also a lot of pressure to go to new solutions. But you've seen, I think, from history in the past that always, if there is some technology that works, people will push it. We still are using oil for hundreds of years, and we will get all the oil which we need it, and we will use it. Although we know it's maybe not the best solution for the Earth as a whole, but we will use it. And I think that's also in parallel, different solutions will be found. And then in the end, one will take over from the other, and then we will see what is the best solution. So, but I think for neuromorphic computing or cognitive, it's different from quantum computing. There, I think technology is really difficult in the respect to get the stability of the qubits. And in neuromorphic computing is still a little bit more close to the traditional computing in a way to make it in devices and into systems. So I think there we have more possibilities to be a bit faster chip technology, because it's still close to the current CMOS technology, and that's not the case really for quantum computing.
But I guess also this is a problem because it's close to the CMOS technology, but it's also close to the CMOS technology in the performance as well. So there is no like a very hard evidence that if you move to neuromorphic computing, you will gain too many advantages. And I guess this is one of the problems why commercialization can be delayed for some time before you have multiple proof of concept for some application that if you move to neuromorphic computing, you will completely outperform CMOS technology.
No, but I think you can also do in CMOS technology neuromorphic computing. That is, I think, what is a bit a mistake. That we really have to get rid of CMOS. Indeed, I think there is not currently a proof that CMOS can be so efficient, all the current transistors, that we can still do, but anything what we have to do for neuromorphic computing, from pattern recognition, to go to new hardware. And that maybe can even be done, we can still call it neuromorphic computer and do it with CMOS technology. But I think there is still an issue because CMOS technology is not optimized for kind of analog kind of behavior. And we need memristors, which in the end can also be analog, or at least multi-level, hopefully 100 states, 1000 states, not fully analog. But and then I think there is a opportunity that it can be more energy efficient and that we can do it. But the point is, the current solutions in the memristors are, from energy efficiency point of view, not as ideal as the optimized transistors we have in our current CMOS technology. So that's why this is not fully solved. But that we have to go to neuromorphic computing, I think that is needed. But how we make the architecture, that is still a bit an open question.
But for example, in Respite here, we are trying to explore different technologies, different hardware, completely different hardware than CMOS technology, to move to neuromorphic computing. So, and I guess many other people, many other groups in different institutions works in different hardware, trying to implement neuromorphic computing in different hardware technology. So I think everyone moved to new hardware, but at the end, like still all of these efforts are more or less in proof of concept phase or feasibility study phase. There is no real evidence that if we use this hardware or that hardware, it will bring a very clear advantage compared to CMOS current implementation.
From the remote participants, are there any interventions on the frontiers of research on neuromorphic computation, and what are the major obstacles as to why the neuromorphic computation is delayed and why we did not achieve it up to now? What are some of the technical obstacles that we need to resolve? I mean, what are some of the key neuromorphic circuit primitives? In our case, we have the neuron, right? Juice switch and the phase change memory dendrites. What are some of those research frontiers that we need to deal with in the future?
I can mention something on the phase change memory. It's really powerful that you can go to multi-level states, so beyond zeros and one. But one of the prime issues is still that it's not, the energy consumption is still not optimal. It's still a relative high, say, currents involved. So in that respect, we still have to find solutions to improve that. But there are also some ideas how this can be done. But that is one of the issues. So that's connecting to the previous, that we still don't have in that respect. We know it can work. But if it really solves a lot of problems in terms of energy consumption for the system, that's still not proven yet. So that is one of the main challenges.
Okay, so thank you for your participation and comments on the future of neuromorphic computation, and in particular our Respite project. And we hope to meet again, I think, about 2 months from now. Our regular meetings will take place, and we'll discuss further the progress of our project. So thank you all for your participation, and hope to see you next time. Thank you. I think now we can